x dy into plus b y x. Yes. So plus prime sharp. So I think we called it 4.192 and said again that rho CP is equal to this one K Nabla squared C plus beta C. There is this manipulation I did when I got to get at this. So I want you to do it and give it to you. Do it and you so I can. I want it in a paper so I can transfer it to this my note. Most of those things will be solved here. So plus mu 5 plus sharp gamma. So we call it 4.19. So sometimes in this situation, you need to simplify. Depending on the cases involved. The first case, sometimes we see in fluid mechanics and heat transfer and thermodynamics is what? Constant density process. That's constant density process. So let me refer to our book so that we had this. So we now have 4.1.1. Can say simplification of the general energy equation. General energy equation of convection, in particular cases. So what are those cases? There are many cases depending on their design and what they are doing. But generally and often, frequently, we normally have case 1. And what is that case 1? Constant density fluid. Constant density fluid. That's I intentionally wrote this from the previous derivation. So I wrote it that way. It's anyone, you can choose anyone. So for us to simplify. So simplification of the general energy equation of convection in particular cases. Let's say this 1, constant density fluid. And what is it all about? Constant density fluid means that the volumetric intensity is what? Equal to 0. You understand? So it shows that beta is equal to 0. Therefore, this is equal to 0. Is that right? Yes, sir. That it also shows that constant pressure is equal to the specific heat at constant volume. Therefore, CV is equal to CV is equal to C. So this equation now becomes rho CP. No, rho CP, the T is equal to K nabla squared T plus mu 5 So we call this equation what? Okay, this 4.19. So I think we should call this equation 420. Is that? Yes. 420. Okay. I can see the previous equation I wrote. That is the full expressions for sigma x, sigma y, sigma z, and all those characteristics in the x, y, yx, zx, and zy contains 4.20a, 4.20b, c, d, e, and f. Okay. So, and I think that this the first case is one constant density free, and we arrived at it. So we call this 4.21. I don't know whether you. So we can call this 4.21. So 4.21. So the second case is case 2. Case 2 is that's the perfect gas, the ideal gas. The ideal gas fluid. Ideal gas fluid. Call it ideal gas. Okay, yeah, case 2. The ideal gas. So the ideal gas has it, of course, from particular law we have E is equal to RT. So if that is the case, we are looking at this. So we have that is equal to 1 over v. 1 over v. Into, I think, this is a volumetric intensity which will give us dV over dt. Okay, yeah. It will give us at constant pressure. So that's the volumetric intensity beta gave us this. So we want to evaluate to know what it will be for a particular, for ideal gas, which will give us 1 over v. That is P over RT is equal to 1 over V. So here becomes P over RT, and here becomes dV P over R. So which is equal to
R over P.
Is it R over P?
Yes.
Okay. Let me dV. That is dV dt
P over the other side.
Okay, that means R should be here.
Yes.
Then P should be here. Thank you. That is P should be here. That is dV dt. Then R over P. So which will give us this and give us that. So finally we now have 1 over t for this case. So if we have 1 over t, going back to that equation, we now have rho cp dt is equal to u prime plus k squared t plus 1 over So this becomes is equal to U plus A plus B plus so we call this 4.2 rows. Hold on. That can be met. There is general simplification that can be made. So other simplification, you can see what is right now. So other simplifications will, just as I was telling you, will depend on the specific, will depend on the specific flows. That's specific fluid flows and geometry. You know, fluid flow is in geometry. Fluid doesn't flow just on air like this. It must be on geometry. And on, like the geometry we are going to treat, as far as this comes, the example he gave is the geometry known as Fourier flow. The one you see in journal diagrams and see. So that's the one we use as example in textbooks, and we use it. And geometries, and on the relative magnitudes of each length. You don't understand what he's trying to say. What he's trying to say in the equation. That brings us to what we call order of magnitude analysis. You know, you derive this equation, you get this equation simplified. If you are not still satisfied, you work on it. If you still need more simplification, you do order of magnitude analysis and eliminate eliminate the ones you want to eliminate. And then, of course, you see that you need more.